Wednesday. Look what I wrote. Okay, so sorry. Good. Okay, so from algebra, we know what the average rate of change of a function between 2 points is, but let's talk about it again. So 1.3 average rate of change. So let's look at a function. So here is my function f of x, and I have 2 points. I have this point and I have this point. Here's point A and here's point B. And I want to find the average rate of change between A and B. How fast is this function changing between these 2 points? All I have to do is draw what we call the secant line, a line that crosses the graph in those 2 points. Secant line AB. And all I have to do is find the slope. Very good. So y of b minus y of a over x of b minus x of a. We don't really write it like that. I would like you to call them x1 and x2. And then what is this height here? What is this height and what is this height? This must be what? 1. F of x1. And this must be f of x2. That's the way we write it. So the average rate of change, of course between A and B, will be f of x2 minus f of x1 divided by x2 minus x1. Very soon after this, I'm going to ask you, does this resemble, I'm going to ask you now, does this resemble anything we looked at before?
Yeah, y2 minus y1 over x2 minus x1.
And there is something called, very important, and it has a special name.
Is that the midpoint?
No?
Distance?
Mm-mm.
Point stuff?
Mm-mm. We calculated it for several functions, and we simplified it.
The difference quotient.
Right?
Yeah.
Okay, so what was the difference quotient all about? Let's look at it just now. It was a point, P, of coordinates x, f of x. And what were the coordinates of Q? What did we say? What was this distance?
H.
Very good. So this is x plus h. And what are the coordinates then of Q?
X plus h. F of x plus h.
Excellent. Very good. So that's what we discussed a long time ago, and where this is what? It's the average rate of change of this function between P and Q. Same idea. Everything the same. So this is the difference quotient, which is the average rate of change of f of x between P and Q. And you'll see, hopefully today, what we are going to do with this. So let's practice from page 123, 124. Let's look at, and you'll tell me which kind of function is this. Would you like to choose? Or I will. I will choose problem 30.
What's the word after?
124. Say it again.
What's the word after f of x?
After f of x? Between P and Q, sorry. So this is the difference quotient, which is the average rate of change of f of x between P and Q. Okay, problem 30 on page 124.
Can I see just the time for this right there?
Oh, maybe I should write it. Let me write it. So the difference quotient, we wrote it a long time ago, but maybe I should write it again. F of x plus h minus f of x divided by h, because it's x plus h minus x, which is just h. And that's the difference quotient. Okay, problem 30. The amount of money A of t, let's copy, A of t, equals 2,000, in parentheses, 1.015 raised to 4t. The amount of money A of t in a savings account that pays 6% interest. So this is the amount of money. 6% is the interest rate, fine. Compounded quarterly for t years when an initial investment, so this is the principal. They already did the calculation for us in parentheses. We are asked to find a few things. Number one, A of 3, so t is time in years. Time in years. We're asked to find A of 3. We're asked to find A of 5. And we are asked to find, after that, A of 5 minus A of 3. And in last step, what do you think they're going to ask us? A of 5 minus A of 3 over 5 minus 3. Okay, so this is the amount that we get 3 years from the moment we deposit $2,000 with this 6% interest rate and so on and so forth. This is the amount we get after 5. This is the difference from 5 to 3 or from 3 to 5. What is this then?
That's the difference that we get.
That's the average rate of change
in the time period.
with respect to time.
Yeah.
Exactly. So on average per year, remember every average rate of change or rate of change has two measurement units, one from the top and one from the bottom. So it's going to be dollars per year, right? So the rate of change between 3 years and 5 years will be whatever per year. Okay, very good. So what type of function is this? Can anyone refresh our memory? There is no x here, there is no x here or variable here, but I see the variable in the exponent. So what type of function is this? It's not linear, it's not quadratic, it's not rational, but what is it? It's not radical. What could it be if the variable is the exponent?
Exponential.
Thank you. Exponential function. Very good. We can work with this by hand. We have to plug it in. So please plug it in y equals, clear, 2,000, left parenthesis, 1.015. Careful because some calculators will disagree with my parentheses around 4x. I didn't put t because there is no t in the calculator, so I had to put 4x. And then, yes?
Are we doing number 1 now?
I'll show you in a minute.
Okay.
Yes, I put the function in, and then I go to second and table, and I want to put in 3, and I want to put in 5. So for the first answer, we get, and you should highlight it. Go to the right and go up because of cents. So 2391.24. 2391.24. The next one is 2693.71. 693.71.
So what did we just do?
We evaluated the function for 3 and 5.
And you put, you went to y equals, and put that.
I put in y equals the function,
Yeah.
and then I went to second and table, and I plugged in 3 and 5. Or you just redo the calculations.
How do you clear your table?
You can clear a table, but you probably don't have the table in the independent. Yes.
So let's go to, yes, you make ask.
Yes. So you can put in the numbers you want. But even after that, you're not, for some reason, we can't clear the table. Okay. So now the difference between the two is 2693.71 minus 2391.24. And then we have to divide that difference by 2. So what was the difference?
$302.47.
How much?
$302.47.
Very good. I trust you. So now divide that by 2. So we get 15,1, what is it?
24.
24. Okay. Per year. So all these amounts, let me also write it here, 302.47. All these amounts, a difference, were in dollars. That's not where I wanted to write it. I want to write it here. But the rate of change, or the average rate of change between those 2 years, of course, has a totally different measurement unit. One more time. One measurement unit coming from the top, which is dollars, over the measurement unit coming from the denominator, which is years. So between 3 years and 5 years after we deposit $2,000, the average rate per year is 151.24. Assuming your calculations you gave me are correct. Any questions? Any questions?
What question is this again?
30 on page 124. Okay, so any questions? Any questions? Okay,
I love the interest in all of these problems.
good.
We not regular society. We don't have it.
Okay, so let's also look at average velocity. Problem 42 on 125. We are given, suppose that in t hours, a truck travels s of t miles. So we have s of t in miles, distance, of course, equals, the formula is 10t squared. So t is in hours. Hours. Good. We're asked to find s of t minus s of 2, part A. S, was it? Yes, 5 minus 2. S of 5 minus S of 2. And in part B, they're asking us to find the average rate of change of distance with respect to time as time changes from t1 equals 2 to t2 equals 5 hours. Okay, so I don't need the calculator for this. S of 5 will be 10 times 25. S of 2 will be 10 times 4. Do we agree? Because I don't want to multiply, it's easier for me to factor out 10. 25 minus 4 is 21 times 10. So 10 multiplied by 25 minus 4, which is 10 times 21, 210 miles. Of course you don't have to do this. It was easier for me to do that without a calculator. So now they're asking us to find the average rate of change of distance with respect to time, which is the average velocity. It's not the instantaneous velocity. It's the average velocity in miles per hour between those 2 points. So the average velocity will be?
S of 5
Very good.
minus S of 2
Awesome.
over 5 times 2.
Exactly. So it's the average rate of change between 2 hours and 5 hours, respectively. Okay, so then we have the top, which is 210. We have the bottom, which is 3. So it's 70. And it has to have, 70 has to have 2 measurement units. One coming from the top, one coming from the bottom.
Miles per hour.
Miles per hour. So did we get the idea of the average rate of change? Do you think we can continue then? Yes? Okay. In the next section, which is 1.4, I'm not going to give you the title yet. So we know it's 1.4, but we don't want to put the title in yet. I know you have it, but I just want to make a point. So I'm coming back to the famous graph. This is a famous graph now. The P and the Q and an X, f of X, and f of X, and X plus H, f of X plus H. So this is the X, and this is the X plus H, and of course this is the H. We had this several times by now. Of course, this is the, what line is this? Very good. So this is the secant line PQ. Okay, now what do we know so far? What are the major topics of this course that we looked at so far? 2 things. We looked at the difference quotient for different functions. And we also looked at limits. Now we're going to put these 2 together to do something with collaboration between the 2, right? So we know limits and how to calculate limits from the left, from the right, from either side. And we know what the difference quotient represents is the average rate of change of a function between 2 points. And now we're going to put these 2 together and let's see what we come up with. That's why I didn't want to put the title in just yet. Okay. So I know that the difference quotient is, again, f of x plus h minus f of x divided by h. So this is the part that we started with the difference quotient. Now I want to put in front of it limit as h approaches 0. And let's see what this represents. Okay, so this is the concept of the limit that we discussed. And this is the concept of the difference quotient. So again, what happens here when h, this h, gets closer and closer to 0? So then this point gets closer and closer to P. So the secant line now gets closer and closer to becoming a tangent line, right? So when I calculate the limit of the difference quotient, I basically say, well, I'm really trying to determine not the average rate of change between P and Q, but exactly the average rate of change, if possible, because it's not always possible, at this point, right? So I'm bringing Q closer and closer to P. The secant line becomes closer and closer to the tangent line. So now, all of a sudden, you're asking me, you're calling me, and you say, look at your odometer and tell me what it says right this second. And I say 63 miles an hour. That's the average rate of change at that particular point. The instantaneous rate of change at that particular point. Now if you say, what is your speed right now? I shouldn't say that. I should say, where are you right now? And I'll say, I'm 100 miles away from Arnold. And then 2 hours later, you say, where are you right now? And I'm going to say, I'm 400 miles away from Arnold. Then the difference in the distance covered over the time elapsed will give me the average rate of change. But if you say, look at the odometer and tell me how much you're driving at right now, that's the instantaneous rate of change of distance with respect to time. But if you want between 2 points, 100 miles away from Arnold and 500 miles away from Arnold, that would be the average rate of change between 100 miles away and 500 miles away. But if you say, look at your odometer, that will be the rate of change at this particular point, which is the instantaneous velocity. So this has a very special name. Here's one special name, and I will write it if the function is the distance. If f of x is distance function, this will give, it's called f prime of x. If f of x is a distance function, this particular quantity at any point in time for any x with some restrictions, if f of x is a distance function, then f prime of x is called the derivative function of f of x, and it gives the instantaneous rate of change. At p, comma, and any point where, and I need to explain this, f of x is differentiable. Okay, this is a lot. Let's go back. Let's go back and discuss this one more time. So whenever I try to calculate the limit of the difference quotient, I get an instantaneous rate of change. No longer an average rate of change, but an instantaneous rate of change, the slope of the tangent line at that point. Number two, this is not a number. It's a function. And this function will determine the rate of change at any point, the instantaneous rate of change at any point on that function, with some restrictions. Not just at p. So now we said that if f of x is the distance function, then f prime is a derivative function of f of x, and it gives the instantaneous rate of change at p, and at any point where the function is differentiable. So this is the condition that I need to explain further. So now I have a way of determining the instantaneous rate of change of a function. It doesn't have to be the distance function. It can be profit. And you say, what is the instantaneous rate of change of profit? And I will find the derivative. Then it can be cost. What is the instantaneous rate of change of cost with respect to time? And I'll find the derivative. So f prime will give the rate of change at any point where there is a rate of change. In other words, where the function is differentiable. Yes?
What is the derivative?
The instantaneous rate of change of a function at any point where it is differentiable. And I'll explain what differential means.
So you only need 1 point for instantaneous rate of change.
Correct.
You need 2 points for average.
For the average rate of change. Correct. Absolutely.
Because-
Yes.
okay.
Go ahead. Sorry.
I was going to say, because is the instantaneous rate of change relatable more to 0 then?
The instantaneous rate of change is the tangent, the slope of the tangent line.
Mhm.
The average rate of change is the slope of the secant line, going through 2 points. So the average rate of change needs 2 points. The instantaneous velocity is at 1 point, which we couldn't determine before. We could not determine the slope of the tangent if we had only 1 point. But now we can, with the limit of the difference quotient. Yes?
To get closer to that point, is this when we go through at 5 and 5.01 and
Exactly.
5.001?
Exactly.
Okay.
Exactly. Okay, So since I had this question now, and I will come back to it if we need to, but let's talk about when is a function differentiable, or when is a function not differentiable. One more time. What does differentiable mean? So a function is differentiable at a point, and I'll write this down, if it has a unique tangent. Of course, it has to be continuous. If it's not continuous, so I'll put that in writing. But, so for example, I have this function. If at this point it has a unique tangent, the function is differentiable. Imagine a b function. What is the tangent here? Negative slope. What is the tangent here? Positive slope. So at this point, the function is not differentiable. It has two tangents. One that is negative and one that is positive. Right? Another situation, a cusp, like between two teeth. This situation is not differentiable because this is a tangent and here's another tangent. Pretty similar with the absolute value function. So, in other words, we cannot determine the rate of change at that point. That's what it means. It doesn't have a rate of change. So a function like this does not have a rate of change here, which means it does not have a derivative at that point. A function like this. So this is a cusp. This is a corner. So this is when the function is not continuous. And there is a fourth one. Here it is. So this is not continuous. And this is a vertical tangent. So, one more time. What is all these? What are they? What are all these examples? This is a function for which I cannot determine a rate of change. If you give me this function and say, find the rate of change at this point, I'll say, fine. Okay. Yes?
But it's only on the point of the cusp.
Only on the point of the cusp. If you give me this function, which is an absolute value function, and you ask me to find the rate of change of this point, I'll say, sorry, it doesn't have one. It's not differentiable at that point. If you ask me to find the derivative or the rate of change at this point, I'll say, sorry, it's not continuous. It cannot have. It has double tangent. It has a tangent here and a tangent here. They're not the same. Here, they are asking me to find the rate of change of the function here. I'll say, sorry, it's undefined because it's a vertical tangent. So in these four situations, you cannot determine the rate of change. It doesn't exist. In all the others, you can. So, ready for some examples? See how this works? So here's I like these graphs in the book. So this is one where they show that over there at that point, the function is not differentiable. And I like these four graphs. This is the vertical tangent graph. This is a cusp. This is a corner. And these are other corners. See, the function has a tangent here and another tangent here. It has two tangents at this point. It's not differentiable there. Okay, so let's look at a few examples. On page 137, 136, 137. Let's start with 40. Yes, this is a very good example. 45. I don't like to select odd number problems because I would like you to work on them, but this is a very important example. 45 on page 136. We're given the function f of x, which is the square root of x, and we're asked to find the function that will give the rate of change, the instantaneous rate of change of this function everywhere where the function has a unique rate of change. Okay, so what is the definition of f prime? How do I determine f prime? And I have to remember how to determine f prime. And it's nothing else but the two concepts that we know so far, the limit and the difference quotient put together. So this is the limit of f of x plus h minus f of x divided by h as h approaches 0. So now we are putting together the difference quotient and the limit operator. They together will give us a function that, if I use it, when I use it, I will be able to determine the instantaneous rate of change of function f of x at any point where the function is differentiable. Okay? So we'll discuss in a moment when the function is not differentiable. First of all, if it's not continuous or it doesn't exist, then the function is not differentiable. Okay, so can anyone give us the first step? I copy the limit operator. Please do not drop the limit operator to the very last step.
Square root of x, we put that in the bigger x.
Good, I'm ready.
Square root of x plus h
Excellent.
minus the square root of x over h.
Very good. So, like with any limit, even if I don't tell it to anybody, I have to do this and I have to plug it in. So when you plug it in, what do you get? What do we get at the top when we plug in 0 for h?
The square root of x. Oh wait, yeah, 0.
Over?
0.
Good, there is hope. It's a function. We're going to get something, right? So what do I do? How do I handle this? It's an indeterminate. Yes,
I just have a quick question.
please.
With the limit of h going to 0, did the book give you that, or did you assume that for?
That's a definition of, very good question. Thank you, if I didn't make it clear. That's a definition of the difference quotient for any function carved in stone.
So our definition of the,
So the definition of the difference quotient has to be memorized.
so our h will always be going to 0.
Yes,
Okay, that was my question.
yes. When we put these two together, we want the limit as h approaches 0. Why? Because I want q to get closer and closer to p, to
Okay,
change the secant line into tangent.
gotcha.
So obviously h gets closer and closer to 0 from either side. Better? Okay, perfect. So then what do I do? What did we do in the past with such a function? And there is only one way. Any suggestions? We will have to, what is the procedure called?
We need to take a point.
We need to, it starts with R.
Rationalize?
Thank you. The what?
Denominator?
There is none. The denominator is already rational. I'm not going to rationalize h. I can't. So we rationalize the, very good. Using what?
These come in denominator? No.
Remember from last time. If I have a minus b, what do I multiply it by?
B plus x?
To get the difference quotient. Yes, indeed, to get the difference quotient. That's the formula. This is how we started. The first day of classes, we reviewed this. Right? The difference of quotient. Good. So then what do I need? Top and bottom.
Square root of x plus h plus
Of course.
the square root of x.
Very good. Awesome. Great. Good. So we continue here. Of course, I ran out of room. No surprise there. Good. Oops, and I forgot 3, 4, 5. Okay, so then what do I get? Limit, do not drop the limit operator. Can anyone give us the numerator? I will write the denominator. But can anyone give us the numerator applying the difference quotient? Applying the difference of squares, I meant. So what do I get? The difference of squares. So what do we get? A minus b times a plus b is a squared.
So x plus h squared.
It's already there, right? I squared minus x. Do you all agree with x plus h minus x?
Yes.
What happens next? Remember, two things, every time we calculate the difference quotient, two things must happen, right? Or this is another step. We have an extra step, we have the limit of that. But there are two things have to happen, right? All terms at the top without h must go away. And eventually, this h in the denominator must go away, right? Somehow. Good. So I have positive x with negative x. And then I continue with limit as h approaches 0 from h over h, the square root of x plus h plus the square root of x. And then, so the first step was fulfilled. All terms without h from the top went away. And now the second step is also very close. What? Or it's happening. What?
The h is going.
Exactly. And now I can drop the limit operator. And what is the answer?
Square root of x plus
The top first, please. The top one. Very good. Over.
square root of x plus h plus square root of x.
We are plugging in 0, correct? We are calculating the limit. That's why I dropped the limit operator, because I'm replacing now h by 0. If I still keep h in there, I have to use the limit operator then.
Square root of x squared. X.
So where does this go when h approaches 0? Perfect. Where does this go?
Square root of x.
Good. How much is an apple plus an apple?
2 apples.
2 apples. Very good. So moving forward and forever, we will remember that the square root of x prime equals
Over 2 square root of x.
So this is something that we have to commit to memory. We proved it. We don't need to prove it again unless you want to. But anyway, so this is done. And we have